Find any horizontal asymptotes of the function f of x equals 3x minus 2 over the square root of 2x squared plus 1. Notice I say find the horizontal asymptotes, plural. The function could have no horizontal asymptotes, could have one, could have two. A function could also have slant or oblique asymptotes, but that's a subject for another video. Now, let's think about the definition of a horizontal asymptote. So we could frame it as an if-then statement. If the limit as x approaches either positive or negative infinity, you'd have to do these separately, of f of x is defined, it exists, and it's equal to, let's call it, let's just say L, then y equals L is a horizontal asymptote. Horizontal asymptote. Okay, so to determine if this function has horizontal asymptotes, we'll have to take the limit as x approaches infinity and as x approaches negative infinity. So we'll say the limit as x approaches infinity of 3x minus 2 divided by the square root of 2x squared plus 1. Now, what we want to do is use the fact that as the denominator of a fraction gets larger and larger, infinitely large, the overall value of that fraction gets infinitely small. So we're going to use the fact that the limit as x goes to infinity of any constant divided by, let's say, x to the power of k. So as the denominator gets larger and larger, the overall value gets smaller and smaller. So as the denominator gets infinitely large, the value of the fraction gets infinitely smaller, approaches 0. So what we want is to be able to apply the limit term by term, where each term, if it has a variable, that variable is in the denominator of a fraction. So we're going to do a little bit of algebra before the calculus. So let's focus right now on this part. We'll hold off on the limit. We'll hold off on the calculus part. So let's see if we could rearrange this or manipulate this so every value of x exists only in the denominator of a fraction. And so what we're going to do is divide both the numerator and the denominator by the highest power of x. And in this case, it's x to the first power. On top, you have x to the first, and on the bottom, you have the square root of x squared, which is also x to the first power. So we'll say 3x minus 2 divided by the square root of 2x squared plus 1 is equal to 3x minus 2, and we will divide that by x. And then on the bottom, we have a square root of 2x squared plus 1, and we'll divide that also by x, but not x. We're not going to write it as x. We'll write it as the square root of x squared, because we have a square root on the bottom, we have a square root in the denominator, so we want to be able to combine these. All right, so what we've basically done is multiplied this by 1 over x over 1 over x, or essentially we multiplied by 1. All right, I should actually put that over here. We could leave that so I don't have to erase it. All right, and of course, it should be, we should note that let's say if x is a positive number, then x is equal to the square root of x squared. Now the square root and the square don't necessarily cancel each other out, only when x is a positive number. If x is negative, well, x squared is always positive. So if x is a negative number, we can't say x equals the square root of x squared, because if the left side here is negative, the right side is always going to be positive. So we need a negative sign here to balance that off. So for negative numbers, if x is a negative number, then the square root of x squared is equal to negative x, or x is equal to negative square root of x squared. But since right now we're doing x, the limit as x goes to positive infinity, we know x is a positive number. All right, so I sort of slant down here so we have some more room. We could split the numerator up into two terms, 3x over x, which is 3, and minus a 2 over x. And on the bottom, since we have two square roots, we could combine them into one square root. The quotient of square roots is equal to the square root of the quotient. And so inside we have a 2x squared over x squared. So the x squares cancel to a 2, and we'll have 1 over x squared. Now this is what we want, because now we're going to take this fact and apply it to this step. So when we take the limit, so now let's apply the limit. So now the limit as x approaches infinity of 3 minus 2x over the square root of 2 plus 1 over x squared. Well, we could split that up into two limits. That's the limit as x goes to infinity of the numerator over the limit as x goes to infinity of the denominator, and we could actually bring that square root out of the limit. 2 plus 1 over x squared. All right, perfect. So now as x gets really, really big, this gets really, really small and goes to 0. And again on the bottom, as x gets really, really big, 1 over x squared gets really, really small. So it looks like we end up with the limit as x goes to infinity of the number 3 is 3. The 3 doesn't change. So we have 3 minus 0 on the top. And we have the square root of 2 plus 0 on the bottom, or 3 divided by the square root of 2. Or if we want to rationalize that, we could say 3 root 2 over 2. So 3 root 2 over 2 is a horizontal asymptote of this function as x goes to infinity. So going to the right on the graph, we have the horizontal asymptote 3 root 2 over 2. Now if we want to look in the other direction, maybe we have the same horizontal asymptote to the left, maybe there's a different one, or maybe there isn't one. So if we take now the limit as x approaches negative infinity, well, we've done some of the algebra already. Now the difference is right here we're going to use a negative square root of x squared, because if x is going to negative infinity, so this is what I was talking about earlier up here. If x is going to negative infinity, or is a negative number, then x is equal to negative square root of x squared. So we'll have a 3x minus 2 over positive x, and on the bottom we'll have the square root of 2x squared plus 1, and we'll divide that by negative square root of x squared. So yeah, we're doing the same thing to the top and the bottom. On the top, we're dividing by a negative number. On the bottom, we're dividing by a negative number, same number. So that's an overall net change of nothing. And it looks like we'll end up with almost the same results. So we'll have the limit as x goes to negative infinity of 3 minus 2 over x. And on the bottom, we'll have the, we've done all the algebra up here in blue. So let me just skip to the last step. We have a negative sign. We have the square root, which could come outside of the limit. The limit as x approaches negative infinity of 2 plus 1 over x squared. So almost identical to what we did in blue with the limit to the right. All right, so that's, again, the 2 over x goes to 0. The 1 over x squared goes to 0 as x goes to infinity. And so we end up with positive 3 on top and a negative square root of 2 on the bottom. Or again, we could rationalize that. Negative 3 root 2 divided by 2. So 2 horizontal asymptotes. If we were to graph this function, one is up here at 3 root 2 over 2. And one down here at negative 3 root 2 over 2. Now, I don't want to go through the whole process of graphing the function. It's going to be, it's going to be a rather long process that I'm going to do in a separate video. But this graph, just because I know what this graph looks like already, it ends up looking something like, I think the x will come down here, across, and then approach this one. So something like this. All right. So the graph is not important, and it's not really in the scope of this problem, but the idea of these limits at infinity, it's one more piece of that general big problem, graph a function using calculus. So we need to know the intercepts, domain, vertical asymptotes, discontinuities, increasing, decreasing, concave up, concave down, inflection points, horizontal asymptotes. So it's on our list of information, of pieces of information we need to graph a function. And in one of my videos coming up after this one, I will go through the process start to finish of graphing a function. All right, that's it for this video. Hope it was helpful.